Consider a double slit experiment with charged particles. These particles are generated from a source M, and there are two slits P and Q with a screen placed in front of them. For any point N on the screen, a particle has probability amplitude to go along path MPN and also an amplitude to go along path MQN. These two probability amplitudes add up, thus giving rise to an interference pattern on the screen. Now suppose we introduce a solenoid between the two slits with the magnetic field B pointing out of the page. The presence of this solenoid affects the interference pattern. One may argue that since the solenoid generates a magnetic field, it would directly affect the charged particles, and therefore the interference pattern will also be affected. However, suppose we make this solenoid very thin and long so that the magnetic field outside of it is negligibly small. When the magnetic field is negligibly small in the outside region of the solenoid, these particles will not be affected by the magnetic field. However, it is observed that even if we make this solenoid very thin and long so that the magnetic field outside of it is negligibly small, almost zero, still the interference pattern is displaced. And the displacement of the interference pattern depends only upon the magnetic flux through the solenoid. This phenomena is known as Aharonov-Bohm effect. To understand this effect, recall that the Lagrangian of a charged particle in the presence of an electric and magnetic field depends on the vector potential and the scalar potential. It does not directly depend on the fields, electric and magnetic fields themselves, but depends on the potentials. We have verified this in the previous video. In the present case, the scalar potential is 0. So the only dependence of the Lagrangian comes from the vector potential. Although the magnetic field outside the solenoid is 0, the vector potential remains non-zero and thus influences the charged particle. To see why the vector potential is non-zero outside the solenoid, assume that the solenoid is aligned along the z-axis. Due to the cylindrical symmetry of the setup, the magnetic vector potential A will be along the azimuthal direction. This direction of the angle phi. Now, if we integrate this vector potential along a circular path around this solenoid, we integrate A along the circular path C of radius r around this solenoid. Then since A is constant along this path and is pointing in the direction of the angle phi, we will get A times 2 pi r, where r is the radius of the circular path. However, using Stokes' theorem, this path integral can be written as integral of the curl of A integral of the curl of A over the area which is enclosed by this circular path. And since the curl of A is equal to the magnetic field, so this becomes the integral of the magnetic field over this shaded region which is bounded by this circular path, and this is equal to the flux through the solenoid. Flux of the magnetic field through the solenoid, we denote this flux as F. Therefore, we conclude that A is equal to F divided by 2 pi r, and hence the A vector is F divided by 2 pi r along the phi direction. Thus, the magnetic potential outside the solenoid is non-zero, and it is easy to verify that its curl of A is 0, so that the magnetic field outside the solenoid is 0. Now let us revisit the setup from a quantum mechanical perspective. This is our Lagrangian. We have a vector potential A, and this is our setup. This vector potential A appears in the Lagrangian through dot with the velocity of the particle, dot product with the velocity of the particle. When we quantize the system, then the amplitude of the particle to reach point n on the screen, suppose we denote this amplitude as alpha. So the amplitude of the particle to reach point n at say time t, starting from point m at time 0, will be equal to the path integral corresponding to this Lagrangian. However, in this case, the only two paths that contribute most to the path integral are paths mpn and mqn. So this path integral will simply be the sum over these two paths. So we will have exponential I over h bar action along path mpn plus exponential I over h bar action along path mqn. Here action along path mpn is integral of the Lagrangian along path mpn from time t equal to 0 to t equal to capital T, and similarly action along path mqn is integral of the Lagrangian along path mqn from t equal to 0 to t equal to capital T. The probability to reach point n will be proportional to the mod square of this amplitude. So the probability to reach point n will be proportional to the mod square of this amplitude alpha, and this mod square, if we take out exponential I by h bar mpn outside, then this will be mod square of 1 plus exponential I over h bar s mqn minus s mpn, mod square of this thing. If we simplify this further, we see that the probability is proportional to 1 plus cos of phi, where phi is the phase difference between paths mpn and mqn, and is given by 1 over h bar s mqn minus s mpn. So probability is proportional to 1 plus cos of phi, and phi is the phase difference between these two paths, and the phase difference between the two paths is the action along path MQN minus the action along path MPN. So let us now calculate this phase difference. This phase difference is 1 over h bar. Action along path MPN is integral along path MPN from t equal to 0 to t equal to capital T of L dt, and L is 1/2 mv square plus q v dot a dt minus 1 over h bar mq, this was integral along mqn, and this is integral along mpn from t equal to 0 to t equal to t, 1/2 mv square plus q v dot a dt. So this can be simplified as 1 over h bar integral, let us write this as simply mqn, integral along path mqn, 1/2 mv square dt minus integral along path mqn, 1/2 mv square dt from t equal to 0 to t equal to n, t equal to 0 to t equal to sorry, not n, capital T, capital T. So this is the contribution to the phase difference coming from the kinetic energy term in the Lagrangian, plus 1 over h bar mqn q v dot a dt minus q mpn v dot a dt. We will not go into calculation of this contribution coming from the kinetic energy term in the Lagrangian. This contribution is approximately equal to the 2 pi times the difference between the lengths of the two paths L2 minus L1, where L2 is the length of the path MQN, L1 is the length of path MPN, divided by lambda dB, de Broglie wavelength of the particle, where de Broglie wavelength of the particle is h over mv. So this is approximately equal to 2 pi the path difference between these two paths MQN and MPN divided by lambda dB. L2 is the length of path MQN and L1 is the length of path MPN. So the contribution due to the kinetic energy term is this, and the contribution due to this vector potential term is 1 over h bar q. This is a dot v, and v is dx by dt. So this becomes a dot dx along path mqn minus a dot dx along path mpn. Now this integral along path mqn minus mpn of a dot dx is simply, so if we write this is the contribution due to the kinetic energy term plus 1 over h bar q. This integral is simply loop integral of a dot dx along the loop m q n p m p n m q n p m. So if we go along this loop and integrate this loop m q n and back p n, integral of a dot dx along this loop is the difference between integral of a dot dx along paths mqn and mpn. So we have this loop integral, and this loop integral is, by Stokes theorem, integral of curl of a in the region which is bounded by this curve, and this is simply equal to the flux through the solenoid. So we get 2 pi L2 minus L1 by lambda dB plus 1 over h bar q times the flux. So the contribution from the magnetic potential is given by q times the flux through the solenoid divided by h bar. This is the contribution to the phase difference between the two paths coming from the this non-zero magnetic potential term. In summary, this Aharonov-Bohm effect demonstrates that even in the regions where magnetic field is zero, the vector potential can still affect the particle, leading to a phase shift in the interference pattern, and this phase shift is proportional to the magnetic flux through the solenoid.